Hi there. Hi, welcome back. We're looking at Chapter 3, Lesson 4, and I want to start solving exponential and log functions with a quick reminder of how we know that two functions are inverses of one another. You can see that we've started with a simple linear function y equals x plus 1, and in order to find its inverse, we switch the values x and y and then solve for y again, which gives us y equals x minus 1. And I started off down here. I'm going to erase this. The way that we know we have inverse functions is by assessing f of g of x and g of f of x. And what we should get in each of those situations, the composition of those functions, is the value x. So let's take this first function, y equals x plus 1, and replacing all values with the other function. So f of g of x would give me y is equal to, replacing the x in the first equation with the value in the second, x minus 1 plus 1, and we can see that function yields x, or that composition. We're going to take the second one, y equals x minus 1, and we're going to replace it with the opposite function, x plus 1 minus 1, yielding x as well. So this is just a quick reminder of what it means to have inverses of each other, the composition of which yields the value x. So as we're getting into solving these exponential and log functions, we want to remember some of the properties of logarithmic functions, and they go back to lesson 3.1, I believe. A to the x is equal to a to the y, if and only if x equals y, and log base a x is equal to log base a y, if and only if, and we write that in mathematics, if and only if x equals y. Now I just talked to you about inverse functions, and we know that logs are inverses of exponential functions, and I want you to see that in this case a raised to the log base a x. These are inverses. So a as a base of an exponent raised to the log base a, those are inverses of each other, and we take this composition and should always get x. In very similar, log base a to the x, this also equals x. Remember, it's asking us a to what power, over on this side, a to what power is a to the x. A to what equals a to the x. Of course, that value has to be x. So these last two examples showing us how exponential and log functions are inverses of each other. In example 1, it says solving simple exponential and log functions equations. It goes through several examples, A through H. We want to look at something like part A. It's saying 2 to the x power is 32. We can do change a base. We can, or change the value 32 to the exponential of 2 to the 5th power is 32. So 2 to the x, remember in our properties, 2 to the x equals 2 to the y if x equals y. So in this case, x has to equal 5. And in example 1, part B, we can solve using properties, addition property of equality. I have log base 4x minus log base 4 8 equals 0. I know that we could add log base 4 to both sides of our equation. And we have another of our properties. If log base 4x is equal to log base 4 8, then of course x has to equal 8. It's always good to think about problems like example 1, part D. We have 1/3 to the x is equal to 9. I want to rewrite these. I see they're both related to powers of 3. In the case on the left, 1/3 is 3 to the negative 1, still being raised to the x power, and 9 is 3 to the second. Well, since we have our bases congruent, I know my property of exponents, a power raised to a power is simply multiplication. So negative 1 times x, negative x, and the power on the second side is 2. And solving for x, we can see x is equal to negative 2. And let's look at example 1, part E. I see e to the x is equal to 7. One of the properties of logs is that we can take, if we have an equation with e or with a log, we know that we can take the natural log, in this case the natural log because we have base e. We can take the natural log of both sides. We've done the same operation to both sides. Now on the left we see e to what power is e to the x. We know this is a inverse, so we know that our solution is x. And on the other side, we just have a simple calculator problem, log 7, and x is equal to log 7, and we can calculate that and get approximation. That's our inverse property. Similarly, problem F, we have log x is equal to negative 3. This is, so we started with e in the first one. We started with the natural log in this one, natural log of x. And what we want to do is exponentiate in this case. E, we're using the inverse property, e to the natural log e, x, gives us x. And we're going to do the same thing on the other side. E to the negative 3. X is equal to e to the negative 3, or x is equal to 1 over e cubed. Example 1, part G, we have now a common log, base 10. X is equal to negative 1. We're going to use our inverse property one more time. We're going to raise this side as a power of 10, and this side as a power of 10, and 10 to the log base 10. Those are inverses. They cancel, leaving us with x. Any function taken at its inverse comes to x, and we know 10 to the negative 1 is just 1 over 10. Part H, log. Now we have a common log base 3, x is equal to 4. We can do the same thing here, but we're going to raise to a power of 3 this time. 3 log base 3, inverse operation. We yield x, and 3 to the 4th, giving us 81. Please go ahead and look at problem number 27. Come right back here, and we'll go over the solution to 27, which is on page 217. So 27 is asking us to solve for x, of course, and I see that 8 and 64 have some common grounds here. 8 is a power of 8, 64 is a power of 8, so I'm going to rewrite on the left-hand side to a power of 8. 1 over 8 is 8 to the negative 1, so we have 8 to the negative 1 to the x, 8 to the negative 1 to the x. Properties of exponents, that's just 8 to the negative x. And on the right hand side we have 8 to the second power. And we know that if we have same bases, then the exponents have got to be equivalent. So negative x is equal to 2. X is equal to negative 2. We're now at the top of page 211. Example 2, solving exponential equations. The first one, part A, gives us e to the x is equal to 72. And we can see that what they've done is taken the natural log of both sides, natural log of e to the x. They've used the inverse property. They've got to take the natural log of 72 on the right hand side. Same thing, both sides. E to what power is e to the x? Inverse property, that's just x. Then the natural log of 72's calculator, it's approximately 4.28, and we can check that. Part B says we're going to take 3 times 2 to the x and figure out what x has to be in order for that whole thing to equal 42. Well, we're going to isolate the exponent part. We're going to divide both sides by 3. So 2 to the x is equal to 14. And now we have our exponential function, 2 to the x. We can take common log base 2 on both sides. Sorry, didn't leave enough room. Again, common log base 2. Well, this is saying 2 to what power is 2 to the x? Those are inverses. That yields x. The common log base 2 of 14. Remembering in chapter 3, lesson 3, we did a change of base operation, and that was taking the log of 14 divided by the log of 2 and changing that back. Now it's base 10. 10 to what power is 14? 10 to what power is 2? And they took the natural log. We can take the common log and see that that is approximately 3.81. Please try number 33 and come right back here for the solution. So problem 33 on page 217 gives us 6 times 10 to the x is equal to 216. We understand we're going to get rid of that 6, get things a little simpler. 10 to the x is equal to 336. So if we take the log of both sides, log of 36, and the log base 10, 10 to the x, inverse again, we end up getting x, and the log of 36. Now we're asking ourselves, 10 to what power? 10 to what power is 36? Well, I understand 10 to the first is 10, 10 to the second is already 100, so we estimate it's got to be somewhere in the middle. And when we take the log of 36, we get approximately 1.56. X is approximately 1.56. If you'll take your calculator and raise it to the 1.5563, that's what I truncated, you'll see that that will give you exactly 36.